realize that you're all survivors. It's the last day, very intense conference, last talk. I'll try to make it even lighter. Probably noticed that, yeah, my second was hardest, but at least I told you motivation, because I know, like, very often when sort of you give very nice talks, or you do this, you get results, everyone is excited, and then you say, what shall I do? And then, oh, how do I do this? How do I do that? At least you will get some flavor where the difficulties are, there are different approaches, and so on. But anyway, so now I will try to make it even lighter, and mostly I'll show you some examples, and we'll share at least where I was most puzzled. So certain things, as I said, it took us like a month to really understand what we are plotting. So of course, the right question, I think, to test yourself, if you want to check if you understand quantum mechanics, you have to ask yourself, what am I going to measure? If you cannot answer this question, it means you don't understand something. So that's really important. And for us, it took a lot of time to digest. But of course, once you digest it, you say, oh, it's trivial. But that's always the case. So let me, before, just say, finally, what sort of Bernardo found. This is really amazing, in my opinion. So he basically, after struggling for, I said, like almost a year with this, how we include noise correctly and so on, he said, wait, but let me actually start from the beginning. So as I said, we are trying to write a path integral. And remember, path integral is basically representation of again, it's a Wigner function, but it's a partial, we are doing partial Y transform. It's an operator in spin space, but it's a function of x and p. So it's kind of combined object. So anyway, it's a matrix. Then we have e to the h while t over h bar. And I put hat. Again, it's a matrix. It's a matrix only in spin space. It's a number in terms of x and p and so on. Then we have some observable, what we want to look at, or while. Again, matrix in a spin space. And we have this. So at the end, all path integral is to try to deal with this term. And I just want to say that at the moment, at least before, yeah, let me just say it differently. So when I try to write path integral, my x and p become time dependent. But this time dependence comes because I'm writing time integral. Otherwise, these are just operators or numbers. They are constants, right? I consider a time-independent Hamiltonian. All dynamics comes from the fact that P moves, like when you consider chemical reaction, right? Yes, ions move and so on, but my Hamiltonian is time-independent. So operators X and P don't change in time. What changes in time is like when you write them in Heisenberg picture. And then Bernardo said, wait, but we have this gauge freedom. Oh, sorry, and I again wrote it wrongly. Right? When I'm of course computing trace of this. And it's trivial, right? When I take trace, I can do any unitary transformation. It's my choice, right? And then the idea, okay, but let's try a meta frame. And after that, write path integral. And what is beta frame? It's beta frame when we are more diagonal in a moving frame. Because I told you, the first step, you are trying to diagonalize H, but then you have problems that states don't overlap. So mathematically, of course, the idea, the best frame would be that such that if you do a while symbol of this object as a function of x and p, its states are x and p independent. That will be ideal scenario. If you manage to find this frame, everything else is trivial. Everything is diagonal. You forget about matrices. But doing this is hard. So let's try to find this frame perturbatively. I just want to say this is kind of the same spirit of Schiffer-Wolff transformation. I'm not doing perturbation theory on states or whatever. I'm trying to do some perturbation theory on the Hamiltonian. And anyway, so before I take saddle point, it's not even approximation. For any unitary is okay, right? It's on approximations will be only when I take saddle point. So, and to make long story short, let's just choose Born-Oppenheimer unitary. So we will choose same unitary which I was trying to do, so the one which diagonalizes this Hamiltonian. But I do it before converting X and P into classical objects, right? So basically, I define U dagger of X, right, times P squared over 2M minus P of X S, and then I do U of X, right? And I just want to highlight, these are all time independent. X is an operator, it knows nothing about time, right? And for this U, I will use Born-Oppenheimer U, which diagonalizes this thing, right? So you might say, oh, but that's exactly what I was doing, right? Because I was saying that, well, what's normal Born-Oppenheimer? We convert P and X to classical variables, and then we try to find a basis where basically S follows eigenstates of X and so on. I'm doing the exact same thing with one caveat. X is time independent here. And then, of course, I can work in position representation where this X is a number. Again, it's an operator, but it's an operator in position representation, right? And P becomes minus IH bar d by dx. I don't have to do it, but this, of course, simplifies analysis a bit. And now I'll say, this is my Hamiltonian. So according to what I told you, you just have to take its Weyl transform. This is new Hamiltonian. But there is a caveat. Taking Weyl transform and unitary transformation, these operations do not commute, right? So deciding which object is classical depends on the frame. It's kind of trivial mathematical statement, but I think it's a very deep physical statement. So what you have to do is to do this. It's U dagger of X star P squared over 2M minus B of X times S star U of X. I skip U. It, of course, works for any unitary, but here I focus on Born-Oppenheimer unitary to be concrete. That's my new Hamiltonian. I have a star product. And now remember what star product is. Star product is U dagger of X times e to the I H bar over 2 times my post bracket operator. Again, this is completely spin independent because I only do Weyl transform with respect to X and P. My spins are my spins, right? And I remind you, this is generally a matrix because it depends on spins, right? Everything here are operators in spin space, but numbers in X and P space. Then I have P squared over 2M minus B dot S, B of X, right? And then I have e to the minus IH bar over 2 lambda, and then I have another U of X. Okay, let's just evaluate this. Instead of evaluating the whole thing, let me do it by parts. First of all, what is B of X term? It's actually not affected by this transform at all, right? Because this depends on X, this depends on X, this depends on X. Here, actually, choice of Born-Oppenheimer unitary is important. If I would have U which depends on X and P, I would also have to worry about this guy. But if everything depends on X, I can remove lambda, because lambda necessarily involves derivative with respect to x and p, but nothing depends on p. So this term is not affected. It becomes b dot s. Good. But now remember, x is classical. It's a number. What about p squared? Well, it's a bit harder. But you know, you know, when it's hard, let's start from p. And then when we evaluate p, we can do p squared. It's like much easier. So let me go to the side. And actually, let me do one more change here before I do it. And for now, you might wonder why. But I will promote p to q. And the reason will become clear shortly. This q, and this I will keep actually p. You will see where it comes. Q is an operator, is my physical momentum. That's what I measure, I'm asking. That's what I measure in the lab. So that's what represented by minus IH bar d by dx. This I will want to call p for reasons which become clear. And again, want to highlight, it took us months to digest, even about notations. So p will be my variable in the Wigner-Weil transform, right? But now my operator q, when I do this Weil transform, is maps to u dagger star p times u. So you see why I want to keep a difference. My q is not mapped to p, it's mapped to something else. That's why I want to have different name for p and different name for q. Right now, p is just variable which appears in Weil transform. There is no dynamics, right? I'm just doing unitary rotation, right? So p is the variable, and q is my original momentum of the particle minus IH bar d by dx, whatever weight I measure in the lab. Okay? So this will be what? It will be u, oh sorry, it's u dagger 1 plus IH bar over 2 lambda, right? P 1 minus IH bar over 2 lambda times u. Now you kind of see why I wrote p, p not p squared or whatever q, first power, because now I can ignore high order powers of lambda. Because remember, each lambda appears with one derivative in x, one derivative with p. There is only one p present, so it means all high order derivatives will disappear. There is nothing else, right? If I have p squared, I will have to worry about lambda squared. So, but because it's the same calculation but more complicated, I'll just maybe flash the answer and you can check it yourself. But for p, I will do it on the board. So the first one is u dagger u. That's one. And believe it or not, we spent some time arguing whether Weil transform u dagger u is one. And so it's like, it has to be one, it is one, but it took a while to sort it out. So everything takes time. And by one, sorry, I mean p, right? Because I have p here. So this one, I get u dagger. Remember, p is a number. I did Weil transform. No more operators. Operators here, number here. I have operators in spin space, yes. But here, p doesn't come with spin. If p would come with spin, I will get spin operator as well. So I get p. Then I will get what? I get plus IH bar over 2 d by dx acting on u dagger, d by dp acting on p. d by dp will not act on u because I'll get 0, right? So d by dx, right, acting on the left, d by dp on the right. And that's it, because d by dp acting on the left will give me 0. So that's all coming from this term. And then I have one more, and then, of course, it will be opposite. Get IH bar over 2, u dagger, p. Now I have to use minus d by dp acting on the left, but on the left only means p, because, again, u is p independent. And d by dx acting on u, right? So that's exactly the reason I spent so much time on Moyal product or whatever, that now we have some practice, we know what it is. Okay? So d by dp acting on p is 1, right? So what is d by dx acting on u dagger? We just discussed it. It minus u dagger du dx u. And you probably slowly starting to see how first part of my talk slowly merges with second part of my talk. Because what appears is a diabatic gauge potential. So we'll get minus, because I differentiate u dagger, IH bar over 2 u dagger dx u u minus, so now I have minus because of this guy, my d by dx acts on u, so I'll get minus IH bar over 2 u dagger, derivative on p is again 1, right? And I get du dx, u dagger u cancels, and what do I get? I get p minus basically a. Again, modulo which frame you are using, u dagger, let me just not talk about this. Actually, you get u dagger ua, but I can multiply by u and u dagger, go back to original frame. Anyway, I don't want to it took us also time to sort it out. It doesn't matter. It's a, but you know, if you write u dagger a u, it's a in a different frame. And as I said, at the end, it doesn't matter which frame you're using. What is important, and again, few months thinking, frame only important when you decide to convert your variables to classical. So that's where the frame is important. After that, all frames are the same. You can apply z-axis along magnetic field, z-axis vertical. It's all the same. Quantum mechanics is invariant, right? So in a way, whether you write u dagger dux or dux u dagger is whether you multiply by u dagger on the left and the right, or you don't. But I don't really want to worry about this. So what we find is interesting, that my physical momentum, so that one which I measure in the lab, becomes P minus a diabatic gauge potential. And now I always like to say this joke. I grew up in USSR, but I guess here you can appreciate parallels without any analogies. So we had a joke, actually, when USSR was much nicer than what's happening now. So we were allowed to joke. And the joke was that, what is a communism, right? The joke was the following. It's Soviet system of governing plus electrification of the whole country. And the joke was coming because that time, like basically more than 100 years ago, it was the main thing, how you basically provide electricity. Of course, this is not, it's only half of the joke. The joke is that what's Soviet government? It's a communism minus electrification of the whole country. So now I'm going to do the same joke, and I will say that it's actually sort of quite interesting. The joke is that I said Q is equal to P minus A, which actually, and by P number, I mean it's P times identity operator, right? It's identity in spin space. That's what number means. My joke is that P becomes Q plus A, right? What did I do? I actually told you that my classical momentum, which is going to enter equations of motion, because I'm going to write saddle point of it, right? Is actually physical momentum plus a diabatic gauge potential. So this is what you measure, that's what enters equations of motion. It's very similar to electromagnetism, right? You all remember P minus A, but there is some vector potential, and we give a certain context. Here there is no magnetic field, nothing, right? And this A, I just highlight, it's an operator in Hilbert space. It's not a vector in physical space. It's an operator which live in space of spins. And I'll show you some numerics which kind of says how it works, and I think numerics is really amazing. Also, Bernardo did numerics. But for now, I just want to highlight that this is the classical thing. Now let me go back to my bucket. I'll add more particles. See, bucket with water or my brick. When I tell you this, you'll say, after some thinking, that I'm telling you really trivial thing. Because why am I telling you? I'm telling that the classical momentum, which satisfies equations of motion, is momentum of the box, say walls of the brick, plus a diabatic gauge potential. It's generator of translations, which is momentum of the particles. So when we go to the bucket, I'm just saying classical degree of freedom is a center of mass momentum. You'll say, yes, I know it, right? But the moment I go to dilations, good luck. And I just want to highlight my molecules, they are quantum, they can be quantum, like water molecules or can be degenerate Fermi gas, right? So, but it actually means that the physical momentum of the bucket is actually quantum. It will experience quantum pressure, quantum fluctuations, and so on. Here, for the same reason, it will couple to spin. And this, for example, immediately resolves another problem with Born-Oppenheimer approximation, which not discussed much, but I told you it violates equivalence principle, charge conservation, but it actually violates uncertainty principle. So Born-Oppenheimer approximation, we say, oh, it's timescale separation, blah, 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 but it's extremely bad. Because imagine I have particle coupled to spin in some rotating magnetic field in some way, right? And suppose initially magnetic field is 0, or maybe I prepared my particle somewhere far and it moves here. And suppose I prepare it in some state with delta x of the order of L, everything is in the box, and delta p is of the order of 1 h bar over L, right? Say I prepared it somewhere in log state, right? And now what I'm saying, well, I'm going to measure spin. If I measure spin with some accuracy, I can actually localize the particle here, right? Because if the spin is here, you remember my particle almost follows magnetic field, right? My magnetic field I can make very strong. So we can say, oh, Born-Oppenheimer is perfect. My magnetic field is very strong, right? So particle almost follows this. And then I detect the particle and I see this particle is within this range. So what I say, oh, my particle is here. Delta x is smaller. What happened to delta p? Nothing, because in Born-Oppenheimer approximation, p is uncoupled. What happened here? Well, my q, which is physical p, which should satisfy uncertainty relation, is p minus a. And what is a? A we discussed. It's gradient of magnetic field times sigma whatever y. The larger the gradient, the larger the quantum noise coming from the spin. So when I measure my momentum in experiment, I will see it will either be, there will be noise, so each time I measure it, I will get, of course, this value, which could be arbitrarily small, but then I get plus minus theta prime, because sigma y is plus minus 1. I restore uncertainty relation. So this thing actually is very meaningful. Then you can probably believe me that q squared becomes p minus a squared. It's the same exercise. I leave it as an optional. So you have to go to lambda squared and carefully count all the terms. And then, of course, it's tempting to say that q power n become to p minus a x n, and this is not true because then you will get quantum corrections. There was a difference and so on. So it's now again something interesting. What I'm doing here, I'm kind of doing expansion in h bar, right? Because I just told you that Moyle product differs from normal product because I have this Poisson bracket in h bar. What I'm getting result which is h bar independent, because we argue this adiabatic gauge potential has a well-defined classical limit. So actually, expansion in h bar led us to something which is h bar independent. And if you trace it back, I probably don't show it here, that what this A is doing, classically, it ensures you do correct you keep correct canonical relations between fast and slow variables. So loosely speaking, Born-Oppenheimer approximation classically means that for, if you say your piston, you go to coordinates, which is essentially a position of fast particle over x, because this doesn't depend on boundary. It always changes from 0 to 1. And then we multiply also momentum by x. So it's a canonical transformation, it's dilation. But this violates canonical relations between fast and slow variables. So violation of uncertainty principle in quantum mechanics in classical language translates to violation of canonical relations. And you can show that you need to add this to slow momentum to restore canonical relations. So once you understand result, you understand, yes, it's not quantum. And actually, as I said, this Moyle product is really amazing. So if you think what we got moving frame Hamiltonian without moving, without any time dependence or anything, right? Because what I told you is that our Hamiltonian becomes P minus A over 2m minus P of x times S, right? So here, P and x are my classical variables. There is no velocity. It's Hamiltonian. We know that, right? So now we can open the brackets. Oh, it's squared. You'll get P squared over 2m. Then you get P over m A. And then we get 1 over 2m times A squared, right? Minus B of x dot S. Again, you will find lots of literature with this A. But everywhere, at least I look, by this A, they mean expectation value of A. It's a number, or it's a function. It's operator. So it's the same notation because kind of average of A is A, so maybe it's unfortunate. But it's a different object. It's an operator. Or it's, if you want, it's a function. It's not expectation value. It's a function of fast variables. But anyway, so let's just think what happens in infinite mass limit. Infinite mass limit, as we know, it's exactly when I have external parameter. I forget about feedback, right? Well, this is just a constant. It doesn't affect fast space. What is this? It's a velocity, right? So infinite mass limit, it becomes x dot. So I recover my moving frame transformation. And this is extra stuff I was talking about. But again, it appears not expectation value, not the metric. It appears a square of a diabatic gauge potential. These are fluctuations. Again, everyone will tell you quantum fluctuations chemistry. No, they're not quantum. These are fluctuations. I'll show you an example. This is normal white noise if you have particles like fast particles like bump you. So it's a thermal noise. So it could be quantum, it could be classical, depending on your state. But this is the effect of fluctuations. So it's all here. But of course, if you have infinite mass, if I have infinite thing, these fluctuations are not important. So, and then I'll just repeat again, the amazing thing for me at least, that not only H bar disappeared completely, it's not here, right? Again, it's implicitly here because ground state of this can know about H bar, right? If I confine particle with harmonic potential and confine it into ground state, my P and X will be quantum. So I can now do a inverse Wigner-Wall transform and convert this P back to quantum variable if I want to. But the amazing thing that we got this moving frame transformation without any time dependence. It's not there, right? It's just somehow quantum mechanics or these rules of quantum mechanics, they know about motion. If you're not surprised, just think again, right? Just did some unitary, some stupid unitary, and I got the moving frame. And again, P will become time dependent only if I start looking into dynamics. I got a function of P and X. This is a Hamiltonian. Okay, and now I think I switched to the screen, so let me just say in words what's going on, and I will repeat myself. So now, this is still exact. And then it's a complicated way to write what we had in new variables. And you say, why do I care, right? Well, I care because in this frame, saddle point is much better. Now I'm not going to pass integral picture, but in this picture, I will be diagonal up to this super adiabatic terms, exactly how I was basically justifying the mass correction. So this is much better approximation. But it's also, loosely speaking, it's actually good because we know in practice we need position velocity, we need position momentum. So missing momentum is a big thing. We miss motion, we miss dynamics. When we add momentum, we're already good. We cover much more, right? So then moving Born, yeah, I forgot to finish. What will be moving Born Oppenheimer approximation? Again, I have it written, but because it's on the slide, I'll just in words. This A, if I move in this rotating magnetic field, will be sigma y, where sigma perpendicular rotation, right? So now what I have to do, I have to diagonalize Hamiltonian for fast particle, which contains both sigma y term and proportional to p, but also original sigma z. So if my B is very big, this is Born-Oppenheimer limit. This is a perturbative correction. I still argued I have to take into account, because if I forget it, I lose some fundamental physics. Like I violate uncertainty relation. But I can treat it perturbatively, right? On the other hand, if B is not very big, then this term dominates, right? And my ground state will be along sigma y. And then you can sort of imagine that if, again, I work along B, that this is SZ, this is SY, so you get 2 by 2 matrix, the dispersion will be square root of B squared plus P squared over M squared. This is non-perturbative. I know some works where people do the same in the context of bilayer graphene, whatever, slightly twisted. You basically, your B comes from band structure. They do 1 over B expansion. And this is much worse. So here you can recover non-perturbative results. So it's again, it's like with Schrieffer-Wolff transformation. If you find perturbatively Hamiltonian, you can still get much better results than you do perturbation theory to the states. And the reason is that the corrections to this, as I said, will be related to super adiabatic transformations. And they, for example, will be 0 if rate of rotation of B is constant. So corrections are not determined by theta prime, but basically theta double prime and things like that. Okay, so with this, I will show some numerical results and maybe highlight again some surprises. And also I will spend 2 slides, so I promised, on counter-diabatic driving, which is related to my second lecture and partly third, and also a little bit to chaos, because I mentioned it's also related to adiabatic transformations, but I will be very brief. So it's actually a version of some talk I gave before. I removed some slides, but I kind of kept a summary of what we already discussed. So first will be repetitive, but it's sort of 5-slide summary of what we just discussed, right? So I thought I will keep it. Let's see if I can operate it. There is nothing, right? Does anyone have a pointer? Or maybe it's off. Oh, it's off. Good. This one. Yeah, it's very weak. I mean, but if you can see it, that's fine. And this one. No, this is probably for screen, right? No, I think this is. Okay, let me try to use this one, right? By the way, I'm very proud of this picture. I created it with ChatGPT. I asked to show a ball moving in a box, and this is like ChatGPT vision of the ball moving in the box, right? So I didn't use ChatGPT for anything else in this talk. So yeah. I actually find ChatGPT is super useful if you have well-defined problem, if you want, but the moment you are not sure, you get garbage. So there is room, like especially I know some students worry what you will do. I think the moment you don't solve technical problems, but you solve creative problems, you shouldn't worry. I mean, maybe 20 years from now it will change, or 10, but not in the near future. Anyway, so what I was to say, wanted to say is that we normally talk about Hamiltonian, and this, of course, sets the rules quantum mechanically or classically for dynamics, like shown in this picture. And then, again, just I want to highlight each time I mention that in classical picture, like a quantum, there are two pictures, Heisenberg, Schrödinger. They're called active, passive. In active picture, we follow what individual particles are doing. But in passive picture, we actually check how probability distribution changes. It's Liouville equation. Mathematically, they're equivalent, but again, you build different approximations, right? You discuss, I know, waves in ocean, you don't want to follow each particle. You just follow probability distribution. And quantum mechanically, it's the same. So you have this Hamiltonian, it sets the rules. And then it also, of course, sets the rules of statistical mechanics. And maybe in the last slide, I'll come back to this again. So, and then what I told you extensively, there is a diabatic gauge potential, which is basically frame transformation, right? It just moves you from one frame to another frame. Frames could be arbitrary, so you get gauge potential, or it's called generator of canonical transformations, or generator of unitary. There are lots of names. But if we are interested in particular adiabatic transformations, so adiabatic transformations which don't change our states, so then I have this adiabatic gauge potential, and we discussed its momentum for translation, its dilation operator for dilations. And then this I also mentioned classically, this just describes canonical transformations, right? So yeah, but I guess this I didn't mention, I just said in words. So if you go to transformation where you squeeze L, but then you have to rescale L, then you can easily check that this gauge potential, it's a Hamiltonian, it does the job for you. So if you apply this squeezing or dilation operator, it squeezes X, it enhances P. Right? And then I kind of mentioned it briefly, but since we still have some time, let me just go with that. Actually, in disguise, a diabatic gauge potential appears everywhere. So it's interesting that this object just was not studied that much. So as I said, when you start perturbation theory, you actually do adiabatic transformations, because if you think, what's the analog of perturbation theory classically, right? Or how you probe, say, these changes, right? You are saying what happens to your eigenstates if you very, very slowly deform the Hamiltonian, because the system follows eigenstates, right? So you're actually saying what is a diabatic evolution. And when doing perturbation theories, normal stationary, you do a diabatic evolution. And then the operator which does it for you, which moves you, is actually a diabatic gauge potential. But we always study its matrix elements, right? We never write it as an operator. So Schrieffer-Wolff transformation, probably many of you know it. Any effective Hamiltonian you get, Kondo problem, Hubbard model, whatever you heard, I don't know, Dicke model, rotating wave approximation for Dicke model, which is, you know, James-Cummings models, whatever. They are all actually secretly, you're applying these adiabatic transformations, and you find approximations for adiabatic gauge potential. So 1/over frequency expansion. Renormalization group and field theories, it's the same. You're trying to rotate your bases. You also do, of course, rescaling of space and time, but you apply iteratively adiabatic gauge potential. So you try to find expansion. Flocky systems, Hamiltonian eigenstates, you're actually doing adiabatic transformations. When you do high-frequency expansion, it's like Schrieffer-Wolff transformation. It's identical. When you do quantum annealing or counter-diabatic driving, this I didn't mention yet, but I'll come to that. You are talking about adiabatic transformations. Chaos and integrability, I mentioned a little bit later, but I kind of already alluded. So these transformations are impossible in chaotic systems, and you kind of know it. So dissipation, well, dissipation, I said all non-adiabatic forces are contained in this gauge potential when you go to a moving frame, including dissipation. So actually thermodynamics, when we talk about like constant on motion on constant entropy curve and so on, we are doing adiabatic transformations. Then I mentioned Born-Oppenheimer approximation, but also it appears in speed limits, geometry, topology, and so on and so forth, right? So it appears a lot. So this I go through quickly because that's exactly what Torov explains. So if you go to a moving frame, we get this new Hamiltonian. So that's exactly what I said. So I'm not spending time in this slide. And this is sort of the work which I advertised. This is Bernarda. Also, Anusha Chandran was involved, my colleague, and Dan Arauz from UCSD, who he was visiting. So this, I mentioned you the story about Steve Gerving. It's not that I worked all 20 years on this question, but I always kept it in background. It's interesting that I worked a lot on truncated Wigner, then a lot on adiabatic transformation, then Bernardo was that who actually realized that you can merge them together. So the question I remind you he asked, like, how we describe classically systems with quantum degrees of freedom, right? And then this is example I already mentioned. So, and one I would say trivial example, it's a bucket with water, trivial in sense intuitively trivial. If you try to solve it, it's complicated, of course. But if you develop your intuition, you kind of know what's happening, right? If you do Born-Oppenheimer approximation, water is always in equilibrium, and then if you're below critical angle, it will just go down, right? So similarly, if I think about, here it's a spin in magnetic field, but it's actually quite interesting. We have several spins in magnetic field. And then I said it's almost Dickey model. Think about spins as two-level atoms. It's just kinetic energy is different, so you get oscillator there. But I believe you can analyze it in sort of the same frame. And Born-Oppenheimer approximation, yes, it works sometimes. I don't want to say it never works, but it actually misses all pseudo forces, all forces which come from the fact that I live in this non-adiabatic frame. And then I mentioned violates uncertainty. Well, it violates equivalence principle, right? Because Born-Oppenheimer force knows about gravity, but doesn't know about added mass. So your inertia mass and gravitational mass within Born-Oppenheimer are not the same. Even if mass correction is small, we kind of believe it's fundamental relation, like uncertainty relation. We don't want to violate fundamental relations, right? And then it's actually, it has lots of problems, Born-Oppenheimer. So, and yeah, now I'm going back to this example which I showed, but now I want to illustrate some sort of pictures, right? So again, here, as you see, it's Q, not P, because I want to differentiate P and Q, as I said. And here, this example, again, we analyze, so you have some rate of rotation of magnetic field, and we chose here magnitude of the field to be constant. Why? Because Born-Oppenheimer is then trivial. In Born-Oppenheimer, nothing happens, right? It's easier to analyze non-Born-Oppenheimer effects. And then, so just to summarize, that's how standard Born-Oppenheimer works. And if you want, when you write, I don't know, equations of motion in some solid, this dh, whatever, dx dt is dE dk, you really do Born-Oppenheimer. So like it appears, as I said, in many contexts. So in Born-Oppenheimer, you treat X and Q classically. Then you assume that spin follows the ground state, and kind of in the beginning gave like more formal justification for this, right? So then you basically ignore higher states, and then you derive your effective classical Hamiltonian's expectation of H, say in the ground state. It could be excited state, right? And then you get your Q squared over 2m minus GB, right? So here B doesn't depend on X, so you get X independent Hamiltonian. So in this sense, in Born-Oppenheimer, you will get that you will move along a straight line, and nothing happens no matter how theta rotates. And you immediately understand, yeah, this cannot be true, right? Because if theta rotates very fast, spin has hard time following, so something should happen. And this is also what I just told you. So essentially, we can say that secretly, when we do Born-Oppenheimer, we are doing basically unitary rotation to instantaneous frame, but where X and P are classical variables. So this I already discussed, so I basically don't want to talk about this. And this is a summary of what I just discussed, right? So that's what Bernard did. Interestingly, independently, same idea, though using Wigner-Weil transform, but anyway, with some caveats, but broadly it's the same idea. Actually, the first who proposed this idea was Shenvi. He was chemist, I think around 2014. I forgot exact year. It was some time ago. But no one picked it up. It was completely forgotten. And then these guys, so Joe Subotnik was the leader of this group, but there were some other famous people like Robert Littlejohn, he's math physicist who works actually in quantum chemistry. They came up with similar idea that you just first do unitary transformation and then go to this Wigner-Weil, and then you get a Hamiltonian which contains this gauge potential. But they didn't know about this variational method and so on. They basically used physical intuition and symmetries to approximate this A. But they also realized, yes, this is an operator. This is not just a bunch of matrix elements. It's a physical operator. But the rest of this approximation, and that's where all the plots are coming, it works exactly in the same way like Born-Oppenheimer. You justify path integral because you're almost diagonal. So basically you say that now moving Born-Oppenheimer is expectation value of this moving Hamiltonian, but I just want to say within eigenstates of this moving Hamiltonian. So it's it's very non-trivial, right? Eigenstates depend on P. So it's not just what people were usually doing. You were taking Born-Oppenheimer states. This is self-consistent states. But the rest is that you just say, oh, this is your classical Hamiltonian. And then I already mentioned that there is a subtlety between what is physical momentum and canonical momentum. And again, I know even if you took electromagnetism, I'm pretty sure you probably memorize it, but there is a lot of confusion. You cannot measure. It's very simple. P satisfies equations of motion, Q or velocity, what you measure, right? So it's kind of interesting. What evolves according to equations of motion is not what you directly measure. I mean, in principle, of course, if you fix gauge, you can measure P. You just see that P is equal to whatever. But it's gauge dependent, even though it satisfies equations of motion. What you measure, Q, is not gauge dependent. It's what. So this distinction is kind of, it's funny. I don't think it's explained well. At least I didn't see this simple explanation in many textbooks. So now I resume from where I stopped, right? I already told you that gauge potential is basically theta prime, right, times spin operator orthogonal to the rotation plane. So here I think it's along x because we move along x and rotate in yz. I mean, but you can choose any other setup. It's just simple. You can rotate in. So here it's sigma x, not because I move along x, but because I rotate in yz, right? So your Hamiltonian contains a few terms. So this is known as Born-Juan correction. Because this is constant, it's the same as you would get normally without all this moving stuff. It doesn't care about anything, it's just a constant. But then you get basically effective magnetic field, and you see this magnetic field, as I said, has relativistic dispersion. So immediately get relativity from the spin 1/2, right? And this relativity modifies, if you want, equations of motion and so on. What all this stuff physically encounters is that because of this extra forces, like inertia forces, spin actually lags behind the magnetic field. And because it lags behind, its energy is not that low. And for this reason, it's kind of harder to go over potential barrier. Or if you want, you slow down, right? Because if you follow Born-Oppenheimer state, your energy is minus B. But now it's a bit higher than minus B. Where this comes from? From kinetic energy. So this kind of stuff knows it. So you will get slowing down. And this is what happens if you plot phase space diagram. And by the way, this particular plot was obtained by Shenvi back in 2014. He analyzed very, very similar setup. I actually didn't know about this when we were working on this. Anyway, so what happens, it's a standard phase space portrait in some units, dimensionless units, P and X, and basically the idea, if you are slow enough, the particle cannot go through. Because of this gradient, if you want, you have really high potential barrier. So, and conversely, if you are somewhere in the middle, you cannot go through like to the left and to the right, you start getting closed orbits. So what happens is that you modify equations of motion. Then there is another very interesting stuff. I didn't have much time to talk about this, but let me just maybe surprise you, but also say it's not that interesting. It turns out that within the same approach, you can also check what happens to off-diagonal matrix element. Because at the end, this Wigner-Weil is matrix in spin space, right? So I can ask, what about if I have superposition of up and down states? But now there is something interesting. Up state moves according one Hamiltonian, right? It's up state of this H moving. Down state along another Hamiltonian. I guess after that, you're not surprised that coherence, again, I want to avoid quantum coherence. Oh, it's quantum because spin 1/2. But coherence moves with third Hamiltonian, which is actually sum of average of HM plus HN over 2. So off-diagonal elements have their own life. And then it's kind of interesting. So what you see is that if you prepare a superposition state, after a long time, you will have basically up particles and down particles moving with different velocities. But before they separate, you actually have interference between them. So it's quantum interference. This is completely beyond any Born-Oppenheimer. And this is directly related to the fact that P acquires spin part. Even so, if you measure physical Q, physical momentum experiment, it actually couples to spin, and you can see interference. So Born-Oppenheimer just misses it completely. But interesting stuff goes on. So suppose now I have two spins, and again, it goes to direction of Dicke model, right? I have a bunch of two-level system. So here we consider they are coupled to the same magnetic field. Think about same photon. But we are considering kind of opposite limit. It's spins which are fast and photons which are slow. I think the other will be also interesting to check. But anyway, I do the same thing, right? Because spins are non-interacting, it's a simple model, right? Then my adiabatic gauge potential is just sum of adiabatic gauge potentials, right? Because when I rotate all of them in exact same way, right? When I change magnetic field, each spin rotates. So my total adiabatic gauge potential is going to be total spin, say again in x direction if I rotate in YZ plane. But when I write my Hamiltonian, remember it's P minus A squared, I get this A squared term, this fluctuation term. And this is exactly this long-range interaction Jamir was talking about. So it's total spin squared. For spin 1/2, it's identity. For two spin 1/2s, it's no longer identity. It's long-range interaction, which precisely gives you squeezing. And now you can kind of stare at it. You can say, oh, I can do the following thing. So suppose, as I move in space, I will try to create some barrier. I guess you can add some external potential for P or control whatever gradient, such that P at some point disappears. Then this term is not important. Now, suppose that B also disappears as I move. This term is also not important. I get only squeezing part. And at this point, well, I guess I'm too fast. But if you stare at this for a bit longer, you will start wondering. I'm kind of telling you nonsense. Because I said magnetic field disappears, but it rotates with finite velocity. And this allows me to prepare a squeeze state. I'm rotating 0, right? How is it possible? Moreover, I have a very big gap, right? Because I'm rotating fast, well, if P is not 0. Even if B is 0, I can have large gap proportional to P. What does it tell you? Well, but then you have to again think, what does this gap means? You have sort of robustness to excitations in the rotating frame. So if perturb a little bit, you will not have transitions. So this actually gap doesn't tell me, you remember, it's not a gap in the static Hamiltonian, it's a gap in the moving frame. It just tells you that you have robustness. And it's interestingly, it tells you that once you turn off your magnetic field, you get a squeezing. But then we actually had a hard time detecting it because it turns out you just say, oh, let's make P 0 and let's measure at this point. But then Q, which is physical momentum, actually has huge fluctuations. So in order to measure it, which basically means that some of the particles will move to the left, some will move to the right. So P stops, but Q is different. So actually measuring it requires some efforts. But at the end, you can come up with a scheme to measure it. But you just need to think about this. Because first you think, oh, it's trivial and so on. But anyway, so this can be done, and this is sort of a cartoon. What's happening, you have rotating. First, you just prepare your system in constant magnetic field. Then it's very easy. You prepare Gaussian wave packet and so on. And then you send it to the period of rotation. And rotation, as I said, rotation, whatever angle, it keeps rotating basically. but the amplitude slowly goes to 0. And yes, you measure it on a computer. Hopefully you can do it experiment. You get spin squeezing. So you can engineer it in this way. And then if you have more spins, you can create better spin squeezing. And it's only couples from the fact that spins couple to motion. So it's one of a mass effect. So if mass is infinite, it disappears. But spins are kind of don't interact. Now I would say this classical system is even more surprising. So here it's a piston with particles, and here everything is classical, no quantum mechanics, right? And then we are essentially trying to solve this problem, but including feedback on the piston. So piston can oscillate, particles move, and then we want to understand how to describe the system. So here you can actually solve just equations on a computer, and that's actually what Bernardo does to compare results. But there, generally, even classically, these problems are known to be very hard. And as I mentioned in the beginning, they're very stiff. Because when you have fast motion, it's very hard to solve equations for this guy. You have to discretize time in very, very small intervals. So of course, here everything is non-interacting. It's doable. But if you have interacting particles, even classically, it's a very complicated problem because of timescale separation. So here we have like a very simple Hamiltonian. Again, I write it Q. It's a physical momentum of the piston, right? Then some potential, which is, say, infinite square well. And then we have some interaction between fast and slow. Oh, sorry, this is spring. I forgot. Sorry. This is spring harmonic potential. And then I have interaction between fast and slow particles, and this is infinite square well, right? So it's a very simple setup, but because spin moves, particles reflect, and so on. Okay, so, and here, this is what we are trying to do classically when we try to do Born-Oppenheimer. We are saying, oh, I want to find trajectories which are independent on position of the piston. And that exactly means the squeezing transformation. So psi is my fast x. We just use x just to separate x and p and q, sorry, position and velocity of the piston. Psi and eta are fast particles, but they have the same meaning, right? Then what I do, for each particle, like for each of them, I can rescale psi to psi over x. Why I'm doing it? Well, because then psi lives between 0 and 1. Then it's simple. So the fact that piston moves plays no role, right? So then, of course, I want to have canonical transformation. I have to replace eta by x. But then, as I was saying, then actually this transformation violates canonical relation between p and psi. It must be 0, but it's not, because psi depends on x, right? D nu psi dx is non-zero. And that's actually where the problem of Born-Oppenheimer appears if we treat it classically. So, as I said, it's a simple exercise. If you say your q is equal to p minus a, then this guy will have right canonical relations with everything. So this is the way to restore canonical relations. That's what actually is secretly contained in Moyle product. So it enforces unitarity in quantum systems, and it enforces canonical relations in classical systems. So, but it's the same idea. My A is now, it's a squeezing or dilation operator. It's function of fast variables. So what happens is that my physical Q becomes canonical P minus function of fast variables, right? So, and now we can do the same thing, but now instead of ground state averaging for fast particles, we just do some Gibbs average, right? So we just follow equilibrium. And then let's see what happens. So this is the result of simulation. So it is real simulation. So you have many particles. And what you see is that you see kind of synchronization. So what happens is as piston moves, the particles which have larger psi, so larger psi closer to the boundary, they want to correlate with p, right? Because we have minus p times psi, right? And particles which are further want to anti-correlate. And so what you see is that the system goes to a synchronized joint motion with actually very little dissipation. So if you will write your normal Langevin forces and random collisions, that's what everyone does when you write actually this Lindbladian or whatever. You just say, let's treat it as a bus or whatever. This will be totally missed. You will describe damping. you will never describe this. And as I said, this is exact numerical simulation. But then, yeah, I'll finish and should I finish on time? But then this is where classical approach really helps, and to us it was like really revealing, is what's the meaning of this P. So let's just look at top plot. So it just shows momentum as a function of time. But now which momentum? So the red line, this is a given realization, no averaging. And that's actually why classical systems are better. Because quantum mechanically, we always compute expectation values. It's always averages. It's kind of harder to understand what's going on. Because we are trying, it's like trying to extract some physics from some moments. It's difficult. So here we have given realization of particles. And the red line is basically measurement of momentum, or say velocity of the piston times mass, this Q. And you see, well, it oscillates, right? But there is also a lot of noise. What is this? This is your Langevin noise, which you normally treat within standard, whatever, this approximation, Cadeira-Leggett bus, or whatever, Lindblad, and so on. What is a black line? It's a sum, it's a P, right? It's a sum of this red line plus this psi eta over x, sum of all fast particles. It has no noise. Noise disappeared. And now, I guess you are not surprised. It's actually P which satisfies classical equations of motion. So this quantum noise is completely fake. So it's noise coming from the fact that you are looking into wrong variable, right? You are looking into fluctuating variable. But what satisfies equations of motion actually has very little fluctuations. If you look carefully, there are some very, very small fluctuations. Eventually, the system is actually chaotic. Eventually, there will be some dissipation and so on, which is beyond this moving Born-Oppenheimer approximation. But you have to wait much longer, and dissipation is much less. So if you do Lindblad or whatever, you'll get totally wrong results, just completely wrong results. Sorry, I said P, it's black, it's blue line. But anyway, it's noiseless. So if you take average of Q, then you will actually recover black line. And that's indeed red line follows this. It includes mass renormalization and so on. They're not the same, right? And then what you will see if you add plus minus fluctuations of gauge potential, that gives you one standard deviation. You see red line is within this one standard deviation. So now, if you think actually what I told you more, you can say, oh, it's actually not that surprising, because what I'm doing, I'm just saying, let's take Q, and let me consider one fast particles. I add psi times eta over x. Remember, psi is fast coordinate, eta is fast momentum. So when this guy jumps, either when psi equals to 0, I fit a static wall, but then, because jumps, I mean eta changes sign, right? My fast momentum goes from plus eta to minus eta. When I do this, I add 0. Nothing happens. When it jumps a second time, actually when I hit a wall, psi equals to x, my eta jumps by 2. So this jumps by 2 eta. But that's exactly the momentum which I give to a fast fall. So when I add this 2, I cancel this effect. So this joint variable actually doesn't get any kick. Again, up to 1 over m squared, there will be some small contributions and so on. But if mass is heavier, this is small, right? So this new variable has no noise. But then you can do same simulation. And now this is truncated Wigner. That's exactly what Jamir was talking about. So it's one quantum, and now it's fake. It's like trajectory, but it's a fake in the sense you have to average. But you can still do it. And now you have the same story. If you look into physical momentum Q, it has lots of oscillations. It's not noisy, it's oscillatory because it's one spin. One spin oscillates. It precesses very fast. But it's a quantum fluctuation, right? It comes from the fact that spin is spin 1/2, and when it's polarized along Z, actually it has a lot of noise along X. This X precesses around magnetic field. This is really what gives rise. So if you average all fluctuations, this is your quantum noise. It's the fact that Sx squared is not 1. Right? But then if you look into this canonical momentum, you see it still wiggles. This moving Born-Oppenheimer is not, but it wiggles much less. So it's actually in the same way like absorb this random noise into right variables, I can absorb quantum noise into right variables. And from this picture alone, you see why it's much better quantum classical variable, because it almost doesn't couple to quantum noise. This is what satisfies classical equations of motion, right? So in the same way, when you consider electron phonon systems or whatever, these are not ions which satisfy classical equations. It's a combination of ions and electrons, right? And that ensures, for example, in chemistry, it's a big problem that when this combination moves, I already mentioned it, charge is almost conserved, so a neutral object moves. But when you do Born-Oppenheimer, it's only ion moves. Electrons kind of follow stuff, and you get lots of problems with charge conservation. And more surprises are coming, and this is work in progress, really, but I don't know if I can say more surprises, but it's already surprising. Just said, okay, let's just forget about dynamics. Let's just try to do the same, but in equilibrium. We are trying to evaluate partition function. No dynamics whatsoever. E to the minus beta h, right? But now let's just try to use the fact that our x and q are basically classical and spins are quantum. So suppose I want to do it on a computer. I want to run Monte Carlo. But when everything is quantum, it's prohibitively complicated, right? I have huge Hilbert space, right? So what I need to do, I use exact same trick. I try to find a unitary where this H diagonal. What I find? Well, I find that I have moving Hamiltonian. Again, this P minus A not comes from dynamics, but from this unitary and then Moyle product. And to make long story short, I'm just saying that now I integrate over x and p, which are canonical variables, right? And I have partition function, which is trace over quantum degrees of freedom, but it contains quantum Hamiltonian, moving Hamiltonian. So equilibrium knows about motion, right? And the interesting thing is that velocity becomes entropic force. So the whole concept of motion is actually thermodynamic. If you think, I mean, first you think it's crazy, but I just want to maybe take a step back. So of course you can write the standard relations, but that's a matter of easy calculation. Just said that P couples to velocity. So if you compute d dp or d entropy dp, you will get velocity, which is P minus A over m. You'll get physical velocity, but average, it's thermodynamics. So first, I mean, just see it cannot be. There's no motion. I just deal with some stupid statistical sum or whatever. But on the other hand, we all know that normal mechanical forces are entropic forces, right? Take pressure. What is pressure? Well, you can say it's entropic force because it's related to derivative of entropy. And sometimes you can even say, I have pressure because particles want to increase their entropy. That's the meaning of entropic force, right? And walls, for example, prevent it. So particles push to increase entropy. And that's exact meaning of this, right? But on the other hand, it's a mechanical force. Because if I attach a spring, right, that's exactly the force I measure. And we somehow not surprised by it, right? But actually, this is a result of Born-Oppenheimer approximation. Because you are saying that fast particles follow equilibrium, you have energy, you differentiate energy, it appears, blah, 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 right? But now I'm just saying the same thing. Well, now my piston is not static, it's moving. And because it's moving, actually my fast particles are just in equilibrium, which knows about momentum. But then why it shouldn't be surprising that my velocity, which is physical velocity, average velocity of the piston, will be also entropic force. But entropic force with respect to momentum. And this is to be continued. But basically it means that if you do quantum Monte Carlo without all these weak transformations, you should be able to extract dependence on velocity or something. And of course it's consists with Born-Oppenheimer. I'm actually done, but since I have 20 minutes, I thought I will spend maybe 2 slides. Actually, some of you asked about the topics, what else you can do with the diabatic gauge potential. So one, very briefly, counter-diabatic driving, another, very briefly, chaos. I don't know if you have questions, or you're mostly silent, I guess. Anyway, we are done after that. You deserve a break. So maybe I'll then continue, and then if you want, I have still more than an hour. You can ask me privately. Anyway, so I'm coming back now to a situation when actually counter-diabatic driving with feedback is super interesting and not studied. Can you design potential for your particles such that basically the system non-dissipatively does something? No one did it. It's very interesting. Can the system be sort of create its own dissipationless or whatever protocol? So here I'm going back to what is studied, is that the idea that I drive external parameters. So again, I'm going back to infinite mass limit, and then in moving frame I have Hamiltonian h minus lambda dot a. And the idea of counter-diabatic is very trivial. I add this pseudo force back as a real force. I mean, it's kind of trivial. If I move an elevator quickly, or a car, my water will splash. Why? Because of pseudo forces. Pseudo forces are pretty real. What do I need to do to avoid that? I introduce gravity, which is real force, which exactly counters acceleration, and my water will be always still. So it's exact same idea. So I exactly counter this, and then in the moving frame, this lambda dot a disappears, right? And then my Hamiltonian just becomes sort of diagonal matrix. So if I realize that no matter how quickly I go, there are no transitions, right? So, but of course, there is always price to pay. And the price to pay is that usually this A is a very complicated object. And then the idea that you find local approximation for it. And there you can use this variational approach, symmetry approach, intuition, whatever various people do. But you basically want to counter some of these forces. And then example, we actually came up with this. It's exactly what happens. I'm not going to do it because I will not be able. Imagine I have glass with water, and I want to bring it across the room. And my idea is to bring it adiabatically without splashing the water. But my wage depends on how many customers I serve. So I want to do it quickly. So what I do, I actually tilt the glass. If I'm skilled, which I'm not, but if someone else is skilled, then if you tilt it in the right way, you actually counter this force with gravity, right? And the water remains still. And then you go back, and then you have perfectly still water. And this is an example of a complex system. Water is very chaotic and so on. But that's an example where local counter-diabatic driving can do a lot of job. And sometimes, even in non-trivial systems, you can eliminate around 90% of excitations for free. Right, so this is basically the example I mentioned. So, and there are lots of applications, state preparation, numerical simulations, adiabatic dressing of quasi-particles, as I mentioned, and so on and so forth. And then, this is actually another student who works in BU. There are many possibilities. One of them is that you also want to optimize the path. Like I told you, a waiter, but maybe waiter wants to navigate like around the chairs. This is like, in quantum language, you want to change a path along which you move. And this is a path where this local approximation works best. And that's actually an open question, how you choose this best path. And a lot of quantum control is actually about that. This I mentioned, this polynomial fitting. And yeah, I think I will skip this. So 2 more slides, and I promise I finish. I also mentioned that these adiabatic transformations are related to chaos. And it's interesting, through them, you can kind of see that there is no such a thing as quantum chaos, classical chaos. There is chaos. And actually, we know this well. I mentioned it. What's chaos in this room? Is quantum or classical? I mean, there are no eigenstates. Collisions are quantum. But if I create tornado, it's pretty classical, right? I can see it. So, and this is, again, it's a question of language. But anyway, so normally, at least standard classical chaos is determined through Lyapunov exponent. And actually, I want to highlight, the moment you start thinking about the air, you just realize this definition of chaos has nothing to do with tornadoes or whatever. Like some people say, oh, butterfly velocity or whatever. it's kind of interesting. Butterfly velocity has zero overlap with butterfly effect. Butterfly velocity is basically a velocity of propagation of information, plus or minus. But butterfly effect is how a tornado will be affected by a butterfly. You need to wait. If you really want to have effect, you need to wait for months or years before you'll see any effect. Because you know, once tornado forms, it's super stable, no butterfly, otherwise we will be great, right? So you have tornado going somewhere, like to some city, you have a butterfly, and you know, it doesn't work like that. So anyway, so there is a lot of confusion about chaos, as usual. So, and then I just want to maybe highlight, we don't really need a second trajectory to realize chaos, right? Lyapunov exponents say, let's consider, basically it's like echo, when you do time reversal, that's what out-of-time order correlation functions, which are popular, or you have two nearby trajectories and so on. But you can recognize chaos right away with your eye, with one trajectory, right? So this already tells maybe it's not about what you see. Then it's known, it's established by some people. I think Tomasz Prazen was the one who had a proof, mathematical proof. It doesn't extend to quantum systems. Like, for example, whatever there is no notion of trajectory, but you can define echo, so essentially propagate forward, backward, and you see what the mistake is in observables. And classically, it's the same. You have Lyapunov exponents. Quantum mechanically, it's polynomial in time. So you even don't have this exponential instability. Then it's even unphysical, because if I ask you, suppose in this room, suppose we even forget about quantum mechanics. They say all our oxygens are like hard balls, which collide and so on with right cross-section. Then I ask you how well you need to prepare two initial conditions to see exponential separation. You can leave it as an exercise, but all resources of the universe are not enough, because you have to create perfect Maxwell demon to a high degree. Because if you don't create perfect identical initial conditions, you separate before even you see exponent. In order to see exponent, you need to start from so close initial conditions that it's... So anyway, this Lyapunov exponent is a mathematical tool, but it has nothing to do with physics, either in classical or quantum, at least many particle systems. And then, why adiabatic transformation center? It's actually very clear from, again, trajectory. So I said quantum mechanically, it's stability of eigenstates. So classically, it's stability of long-time trajectories. This is an example of some nonlinear system of a trajectory, and left plot shows one Hamiltonian with omega 1 and omega 2, so it's 2D oscillator equals to 1, and right with slightly different omega 1, just random number. So it's basically almost identical Hamiltonians. You start with the same conditions, you see almost identical trajectories. Suppose I didn't tell you any other information, ask you, is it chaotic or not, and you'll immediately say, no, it's not chaotic. And you can see it in two ways. A, you see with your eyes that it's pretty regular, right? It's repetitive or whatever. But B, you also see it's very stable. Because I changed the Hamiltonian, you see it's almost the same, right? So you see two things, and both things tell you that you don't have chaos, right? Now I can take the same system, but a slightly bigger nonlinearity. I have exact same two pictures, and now you immediately say it's chaotic, right? And then, again, there are two ways you can recognize chaos. A is that, indeed, you slightly change Hamiltonians, you get totally different patterns. But B, even if you look into one of them, you see it's pretty regular. So now the question is, what is the object which knows both about irregularity and instability? And I guess by now you can guess, yes, it's a diabatic gauge potential. I'm not claiming it's the only object, but it's definitely the object which knows about this. Or if we want to be more fancy, I can say it's quantum information geometry with the caveat that there is no quantum in these pictures, but you can apply it for quantum. So essentially this I discussed, and actually this pictures came from two students at BU. I was not really involved, but I really liked it. So they said that, okay, let's even forget about quantum mechanics or classical mechanics. Let's just think about some maps. So you can have some stochastic processes or map and so on. Then what is a diabatic gauge potential? Well, morally, as I said, it's like time integral of your perturbation as a function of t. So you have to remove delta function. You can do it by doing the sign, but they just basically said you can subtract the average. It doesn't matter, it's the same. So then what is geometric tensor? It's norm of this adiabatic gauge potential. It's this time integral squared. And then you average over initial conditions, which could be the one trajectory or distribution, eigenstate, many eigenstates, and so on. And then if your system is integrable, then it's collection of periodic trajectories. And then this integral converges, right? If you have a sine, integral of sine from 0 to t is a constant of the order of 1. So, and this tells you that chi is constant. Now, white noise or short time correlations, that's what happens in ergodic systems, right? You forget memory, Markovian systems, whatever, right? ETH, if you are like familiar with quantum language. Then what happens, you have short range correlations. Then integral over t1 minus t2 gives you a constant, but overall integral diverges. So it diverges as time, right? But if you have critical subdiffusive, so you have very slow correlations, this diverges in a stronger way, right? And maximal divergence is actually 2 when correlations barely decay, right? So when you have logarithmic. And then you just see from this point of view, maximal chaos is actually low frequency noise. And that's actually exactly what your eye recognizes. So if you show white noise, for a short time you see it's chaotic. For long times you'll see straight line. If I show you colored noise, even for long times you see these fractal patterns, you see it's chaos. So when your eye sees that it's a regular trajectory, you actually recognize low frequency noise. And this is again example actually from my colleague Anders Sandek. It's simulation of phase transition, someone mentioned it. Classical, no, it's temperature, right? So this is at the critical point, you form this kind of molasses. And these are, if you want, like tornadoes. They're super stable in time, but try to predict them. Good luck. They're extremely unpredictable. If you want to wait long time, you will not be able to say anything about them. You will be able to say much less than if the system is ergodic. Because even ergodic, you know variance. I mean, you can use statistical mechanics, right? So, and this is my last slide, I think. I think it's the last. Anyway, so this quick summary, of course, I could spend a whole hour on this, but quick summary of this that, yes, fidelity susceptibility, it knows about low frequency noise, but it also knows about instability of eigenstates, or if you want in classical language, instability of canonical maps to map trajectories to each other. So it's very, very difficult to map these trajectories of different tornadoes to each other, find canonical transformation which convert one to another. Much harder if the system is ergodic. So and always, like if you think about some integrability breaking perturbation or temperature or something like that, and this could be a horizontal axis system size or time scale or something, then if integrability breaking is small, we have low temperature, you're always integrable. Then you go to super chaotic regime, which is extremely unstable, and only then you get ETH. And all MBL community, respective to what people believe about localization, they completely miss that. And all this basically theories of MBL, they are all wrong because they just forgot this. They didn't realize that when you go from localization, say integrable to ETH, there is a huge phase in between. And now I had this discussion with several people, including actually Subir Sajdev, who was there, and somehow they react, I wouldn't say angrily, but antagonistically when I say, okay, actually SYK model is not that chaotic. It's very ergodic and so on. I'm saying crazy. But let me actually say it's not that. It's because, again, we often confuse what is chaos, what is ergodicity, and this adiabatic gauge potential can fix that. So suppose I have a spring or spring with a mass. And suppose I go outside of this room to someone who never studied physics and ask, is it chaotic system or not? Well, we will say it's not, right? It's what we show in elementary physics. We have oscillations, we can predict everything, some dissipation. And then I show some turbulent air or like flame. Everyone will say it's chaotic. But now let's think about what is a spring? It's actually a collection of electrons. We relax almost instantly on like picosecond or femtosecond scales. So if you want to study, I don't know, OTOC or whatever relaxation function, it's super quickly relaxing system. It's very fastly thermalizing. But because it's fastly thermalizing, it's actually not chaotic. SYK model, if I can create spring out of SYK model, it will be instantly thermal. It basically means I always follow equilibrium. It means I'm always adiabatic. I can never create a vortex, tornado, dissipation, whatever, nothing, right? That's why it's actually much harder to create tornadoes in the ocean than in the air. Like on the surface, you can do it, but again, it's where if you are deep in the ocean, you can, I don't know, flap as many butterflies as you want. You create ripples, but you will not create a single tornado. If you go to air, it has much longer relaxation times, right? It's much closer to integrable limit. And actually, it's more chaotic. And this was missed, I think, by entire community. What is chaos? And, well, I have to say, of course, people who studied low-dimensional model, they knew, no, mixing, weak mixing, or whatever, there's hierarchy and so on. But in many body systems, it was missed. Anyway, I don't know. It's a summary for this particular talk, but I guess to finish, I remind you we talked about mostly about Wigner-Weil transform, how you can think about quantum classical connections. We talked about adiabatic transformations, and maybe I'll try to say there is a lot behind and a lot of open questions, really, more open than closed. And then now we kind of talked how you can merge them together. And then, so both concepts sort of give us an entry to understand, if you want, systems, dynamics of systems with timescale separation, or at least gives a new angle how we think about systems with timescale separation. So with this, I thank all for staying until the end and hope you enjoy your weekend and have fun. Okay.
Thank you for the great lectures. I have a question about something you mentioned in the previous one about the path integral including spin.
Yes.
So normally when you do the many-body path integral, you use coherent states.
Yes.
And then it seems that there is no issue with having, let's say, two flavors of fields for up and down spin. So is the issue here the fact that we care about a single particle, or what's the
No, the issue
difference?
is that I don't know how to take saddle point, because you see, I want to take saddle point with respect to x spin, but not with respect to spins. If I do what you suggest, you actually recover full truncated Wigner with Jameer used. Yes, you can recover truncated Wigner for spins. But I was kind of emphasizing, what if my fast degrees of freedom are really quantum, which means that I cannot take saddle point, right? Then I have to deal with basically taking saddle point with respect to x and p and converting remaining path integral back to quantum mechanics. And very likely it's doable, and I will reproduce these results, but I don't know how to do it. It's like very, very complicated. But other than that, yes, you're right, path integral is exact.
Hi, thank you for nice lectures. So I'm interested in knowing if, is there any research done about adiabatic transformation in spirit of Lie derivative, like that you could do, I don't know, adiabatic transformation in translation, then some rotation, and then try to go back, you know? So, because if you're on a non-flat manifold, you not necessarily go to the same point.
Yes, 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 but this is about already like Berry curvature. So this already, you see, this gauge potential is as non-abelian it can be. It's always non-abelian, right? Because this is a massive operator, right? So usually when you ask these questions, you ask about adiabatic limit, ground state projections. And then, yes, this is generator of Berry curvature, and this Berry curvature really tells you about what you are saying, right? So what I think is interesting to do, which I don't know, I don't think anyone did this. So you can study moving geometry, right? So if you now study not static ground states, but ground states XP dependent, can you actually have topological transitions as a function of P? Or can you define a trajectory in XP plane, phase space trajectory, right, which circles around, and you pick up non-trivial Berry phase, Berry curvature, and so on. I think this is super interesting. I don't think it was done, because it kind of goes beyond. It's towards dynamical geometry, right? Because it's geometry which depends itself on the motion. All work, as far as I know, was done on static geometry, like ground states and so on. But then in linear response, it appears, right? So when you just slightly perturb, so you measure conductivity and so on. So this is sort of dynamical geometry, and you can get more interesting results. But this has not been done, so I cannot. And many people are excited by this right now.
Thank you.
Okay, then thank you, everyone. And as I said, enjoy the rest of your time in Brazil.
Now, since I am the last man standing,